Hello, we are 신준영, 강지우, 손정은, who are presenting under the theme of comprehension of performance of cosine functions with or without Chebyshev polynomials. The table of contents consists of the introduction, the main body, and the conclusions. The Taylor series is a method of finding a form that approximates any function in a polynomial manner to approximate the actual function, and is used in many software libraries to calculate the function value of the transcendence. In most cases, the function is approximated near x equals 0, so the greater the absolute value of the input value, the lower the precision. Also, if you increases the order of the Taylor polynomial to increase the precision, the amount of computation increases and the execution time is longer. Meanwhile, Chebyshev polynomial is the polynomial field that appears in the identity of the trigonometric function. This allows for the same level of precision as small inputs for large inputs, but requires additional time as the calculation requires repeated operations. Therefore, we would like to find an optional function with a combination of the Taylor polynomial and Chebyshev polynomial to maximize precision and minimal execution time.
From now on, I'm gonna explain background information which is essential to understand our research. There are two main concepts. The first one is the Taylor series. Taylor series is a way of representing any function f with a polynomial with infinite terms. It is defined as shown. Generally, Taylor series of f is sum of nth derivative of f a over n factorial times x minus a to the n for all natural number n. There are two examples of Taylor series right here. Sin x can be expressed as negative 1 to the n over 2n plus 1 factorial times x to the 2n plus 1. Similarly, substituting 2n plus 1 from sin x into 2n derives the Taylor series of cosine x. Next one is Chebyshev polynomial. It is defined deductively as shown. For nth Chebyshev polynomial Tn of cosine theta is equal to cosine n theta. In our research, we first implemented a function that can calculate cosine using various degrees of Taylor polynomial and Chebyshev polynomial. And then we compared those functions in respect of accuracy and efficiency. To evaluate the accuracy of the function, we compared the value of the function under its 10th decimal points with cosine function from math.h. Lastly, we compared the runtime of the functions while iterating them for 10,000 times. These are some of functions we've actually implemented. Function cosine underscore Taylor gets double x and integer n as parameters. It calls function underscore cosine underscore Taylor, which calculates the actual value of the nth Taylor polynomial of cosine. Function cosine underscore Chebyshev gets double x, integer n, and m as parameters. It calls function underscore cosine underscore Chebyshev, which calculates the actual value of the mth Chebyshev polynomial with the nth Taylor polynomial of cosine.
This is the result of accuracy by comparing the output of the cosine underscore Chebyshev function with the cosine function of math.h. We calculated the percentage of accuracy up to 10 decimal point. And this is the result of runtime by counting the time of implementing the cosine underscore Chebyshev function for 10,000 times. In the result of accuracy, we can see that it gets more accurate as there are more terms, which was what we predicted before running the program. However, about the term of Chebyshev polynomial, which we put as m, we can see that the accuracy decreases as m is 1, 2, 3, and then increases after 4. Unfortunately, we couldn't find out why. Now, as a conclusion, we found out that the best combination considering accuracy and runtime is when n is 6 and m is 4. It is the combination that took the shortest time among 100% of accuracy. Moreover, we want to continue further research about the factor of this inconsistency in Chebyshev function and see how this affects the results of the performance. This is the bibliography, and thank you for your attention.